In this video, we'll talk about statistical analysis and how it can be done with Python. So far, we learned how we can organize our data, how we can transform it, and how we can visualize it. What we're doing now in statistical analysis is asking and answering questions about our data. And our data we usually refer to as a sample because it doesn't represent all of the data, but it's randomly sampled from a bigger population. So for example, we might measure the height or age of people, and we obviously cannot measure every single person, so we're just working with a sample which is a subset of this population. So far, when we worked with our data, we did actually already ask some simple questions. So for example, what is the mean, max, or the standard deviation? And these kind of questions fall under descriptive statistics. So essentially we're describing our data. As an extension to descriptive statistics, we have inferential statistics. And this is where we make conclusions about our population based on our sample. So we use our sample to find patterns and relationships, and we also want to know if these patterns and relationships are significant. So if we can make a conclusion about our population. To give you a concrete example, we talked about measuring the mean height as part of descriptive statistics, and now with inferential statistics, we could, for example, ask if there's a mean height difference between men and women in our population. And we would then answer that by first getting a sample, then applying some statistics to this sample, and then we can draw a conclusion about our population. We said that statistical analysis is about finding patterns and relationships. And now you might ask, isn't that what we're also doing in machine learning? And you would be correct in that machine learning and statistical analysis are very closely related fields, since both are about analyzing and extracting knowledge from data. And there are even some techniques such as linear models that we can count into both areas. Now, the difference is that the predictions and inferences that we make in statistical analysis are more formal and aim to uncover the underlying mechanisms and relationships in the data and assess their statistical significance. And now in machine learning, we care more about the prediction accuracy and building models that generalize well to unseen data. And usually also the models we have in machine learning are more complex, so they are able to capture more complex relationships and patterns. But as the complexity rises, it also becomes harder to interpret our results and also difficult to know what the actual relationships are. Okay, so let's get started with inferential statistical analysis. In order to make conclusions about our data, we have two central techniques, which are hypothesis testing and statistical modeling. Statistical modeling helps us in two ways to answer questions about our data. The first one is that we can model the underlying structure and patterns of our data. So for example, we could model the relationship between two variables. And now if we want to verify that an effect of a variable or some relation between two variables is significant, then we can make use of hypothesis testing. And as the name suggests, hypothesis testing is about testing a hypothesis. So this hypothesis can either be about the relationship between variables, or it can be a statement or a proposition about a population parameter. So for example, we could say as a hypothesis that the mean horn length of unicorns is greater than 10 centimeters. Now to test this hypothesis, we formulate a null hypothesis, saying that there is no effect. Or in case of the unicorns, we would say that the mean horn length is 10 centimeters. Then in the next step, we build a model based on this null hypothesis and use it to generate samples to estimate the data that we would get from a population where there is no effect. And this is the second use case of statistical modeling. And once we generated enough samples, we can compare the samples with our originally measured data to see how likely it would have been to observe our original data in a world where there was no effect. And if it would have been very unlikely, then we can say that there probably is an effect. So the effect is then probably real and not just due to chance. So to give you some intuition with the unicorns, let's imagine we build a model that we can use to generate unicorn horn lengths, and we would base this model on our null hypothesis, so that the mean horn length is 10 centimeters. Now as we generate data from this model, there will be cases where we get horn lengths that are greater than 10 centimeters. So maybe 50% of the times the mean will be greater than 10, and then let's say 20% of the times the mean will be greater than 11. And as the mean increases, of course, the likelihood goes down. So now we turn back to our original measurement. And now let's say that the mean that we observed here was 15 centimeters. and we check our model and we see that getting a mean of 15 centimeters has actually a really low chance. And so then we can say that this model, and so also the underlying null hypothesis, are probably not good models of our world. So we reject the null hypothesis, and we can say with some confidence that probably the mean length of unicorn horns is in fact greater than 10 centimeters. Don't worry if you didn't fully understand all of this, because we will come back to it with some very simple examples and also code and some visuals. Okay, now let's get into how we can do all of this with Python. And we're starting off with statistical modeling. When we're doing statistical modeling, it usually involves the following steps. First, we look at our data and see if there's any structure or pattern that we can identify just by looking at it. And if there is something that we can see, or maybe we still want to ask the question, if there is something that we don't see, then we go on to select a model. Then we fit the model on our data so that the model captures the underlying structure. And then in the final step, we evaluate our model to check if the pattern that we found or the relationship is actually significant. And this will be done with hypothesis testing. Okay, let's check out our data. Our data consists of 100 samples, and each sample comes with 2 values. The x values range from 0 to 10 and are equally spaced because of linspace. And then we take this x, multiply it with a slope, add an intercept, and also some noise. And if we plot that, it looks like this. And clearly there's some structure in this data. So as x increases, so does y. And we actually know what the relationship between x and y is, because we defined the slope and intercept here, but we just did so that we can check if our model can also identify the structure, so these parameters. Okay, now onto our model. And as you can imagine, there are a lot of models that we could hypothetically choose to model our data. But in this video, we'll focus on the linear regression model, which we consider as the fundamental model of statistical modeling due to its simple nature and because it serves as a building block for the more complex models. And the general form of the linear regression model is rather simple. So y is the dependent or the predicted variable, and x is the design matrix, which contains the independent or predictor variables. Beta contains the parameters, and e are the errors. And we could also rewrite this. So first step we have beta 0, which is our intercept, and then for each of the features of our data, we have one parameter. So looking at our data set here, x is just one column, so we also only need one parameter besides the intercept. But if we had more columns, then we would have one parameter for each of them. And at the end we have our error, which we assume is normally distributed. And this error term acknowledges that even if we have a perfect linear model, so in this case a straight line right through here, not all of the data points would be on this line, but slightly off. And how much they're off is modeled by this normally distributed error. Now, when we fit our model to the data, we want these errors, or also called residuals, to be as small as possible. And in Python, this is simply done by using the statsmodels package. So we import from the statsmodel package the .formula.api, and then linear regression goes by the name of ordinary least squares, short OLS. And to this function, we pass our data and also the relationship that we want to model. So here we want to predict y based on x. And then this gives us our model, which we then fit using the .fit. So we run that and then call .summary, and this will give us a lot of numbers. And currently the ones we care about are under coefficients. So here we have our intercept and we have our x, which represents our slope. So the 1.97 here means as we take one step in the x direction, the y direction will increase by 1.97. We can also then plot the regression line by taking from the fit the parameters, intercepts, and our slope. And we can see here in red that's our regression line, and then in blue that's the underlying linear model that we use to generate our data. And you can see these lines are very close to each other, so you can say that our model makes for a very good fit. Alright, next up there's an exercise for you. In this exercise you can load the tips dataset, and your task is to explain the amount of tip that was given based on the total bill. Once you're done, you can check the solution in this file here. Okay, now a very important note. When we fit a model, it's important that we don't just look at these numbers, but we should also always look at our data and see how the model is actually fitting it. So in here we can see 4 examples, and in all of these the fit of the model is actually equally good, and also the mean and standard deviation are the same, but still the datasets are clearly different, and besides for this case here, we wouldn't say that these models are a good fit. So always plot your data and don't just rely on the numbers. Now, of course, the numbers are also important, and it's even more important that we can understand what the numbers actually mean. So far we looked at the coefficients here, the intercept and the slope, but that's not the only thing that matters. So until now we can say we found a relationship in our data, but we're not sure yet that this relationship is actually significant. And for that we can check out the p-value here. And the smaller this p-value is, the better. So actually here we have values of 0, which means that our coefficients are actually very significant. And what the p-value measures is the likelihood of us observing this relationship by chance, with the assumption that there isn't actually any effect or relationship. But the p-value is not the only thing we should care about. Another important value is the effect size. And this is the magnitude of our coefficients here. So our slope here is close to 2, which we can argue is a significant effect size, but also here we cannot be sure because we don't know the units and the context of this measurement. So to give you an example, let's say this here captures the amount of time saved for each 100 euros that you invest into a bike. And to further establish the context, let's say we're measuring that time based on your way to work. And now if we think about the units, if this was minutes, so you save 2 minutes and maybe the total amount is 10 minutes, then we could say this is somewhat significant. But if the unit for this measurement is milliseconds or even microseconds, then we wouldn't say that there's a significant effect. Another interesting value here is the r-squared, which measures the explained variance. So our original data varies somewhat uniformly in both the x and y direction, but now what we see in this plot here is the variance of the residuals. So we fit our linear model to this data, which gives us the line 3 here, and then in here the residuals are the distance of each data point to this line, so our error. And we can see that the variance got much lower. So with our model we explain some of the variance in the y direction. And how much variance got explained we can check by dividing the variance of the errors, so the residuals, by the total variation of y, and then subtracting all that from 1. And this gives us then our r-squared, which in this case is 0.97. So 97% of our variance got explained through our linear model. And this is also the value we can see up here. Okay, so this was the first part of statistical modeling, where we check if there's some relation between our variables or in general some pattern in our data. And implicitly we also did hypothesis testing already, the hypothesis being that there is some relation, but in here Python did all of the work, so it gave us the p-value, telling us that the relationship is significant. Now, how do we do hypothesis testing by ourselves? Now, if you learned about statistics before, you probably heard about the t-test, f-test, and probably many, many more. And what these kind of tests do is that they analytically compute the p-value. So by plugging values into some equation, we get the significance of our effect. And because these tests have so many names, you might think that there's a lot of different ways of testing the significance, but actually they all work the same. So we have our original data to which we apply some test statistic, and test statistic refers to the statistical value that we're testing for. So this can be a mean, median, or a correlation. And then we formulate our null hypothesis and define a model based on that. And then we use analytical methods to compute a p-value, which then tells us if the test statistic of our original data is significant or not. And what all these different names refer to are not different procedures, but they just refer to different kinds of modeling the null hypothesis, different test statistics, and also different analytic methods of computing the p-value. And back when computation was slow, having these different analytic methods was very important. But nowadays we don't have to analytically compute the p-value based on our model, but we can just use the model to simulate data. And then we apply our test statistic to the simulated data, which gives us a distribution from which we can then calculate our p-value. And now the benefit of this computational method is that it doesn't matter what kind of test statistic you want to use, so we could just swap this out and it would still work. And also, as we will see, this computational method is very intuitive. So we don't have to think hard about any of these other tests, and if we're meeting their assumptions. Now, if this graphic looks a little bit complicated, don't worry, because we will get into a very easy example. But first I want to point you to two resources. The first one is a blog post that is called "There is still only one test," which also explains why we don't have to rely on these complex tests anymore. And then there's also a really good talk titled "Statistics for Hackers" by Jake Vanderplas at PyCon that also does a very good job at walking you through the general idea and also gives very good examples of how we can simulate our data. So there are actually some different methods of how this can be done. We have direct simulation, shuffling, and bootstrapping, and in this video we'll cover shuffling, and if you're interested you can also find a section on bootstrapping in the notebook. Now let's get started with our example. And the data that we're working with is about mushrooms. So there are two mushroom kinds, a brown mushroom and a rainbow colored mushroom. And for both of these mushrooms, we have measurements about their psychedelic effect. And now the question that we want to ask about our data is there a significant difference in the psychedelic effect between brown and rainbow colored mushrooms? And so based on the data that we collected, we can calculate the mean for both of these mushrooms. And from that we can calculate the difference, and it comes out to be 0.66. And now the question is, based on our data, can we say that this is a significant value? So our hypothesis will be that there is a significant effect of the mushroom color on the mushroom's psychedelic effect. And the null hypothesis to this is that the color of the mushroom doesn't matter. And the way we're going to model this null hypothesis is by shuffling our values. Because if the null hypothesis holds true, so there is no difference in psychedelic effect based on the mushroom color, then we should be able to just swap around these values and it wouldn't matter. So we will shuffle around our data, then calculate the mean of each group and then also the difference, and then we will store this value to slowly build up our distribution. So the values get swapped, the mean gets calculated, then the difference, and we add that value to our plot. And we're going to repeat that a couple of times until we have a representative distribution of these values. And now we can check back to our 0.66, which was the mean difference when we actually care for the mushroom color. And now we can answer the question, how likely would it be to observe the 0.66 or a larger difference value if the color of the mushrooms didn't actually matter? And we calculate this value by checking how many times in our shuffling runs the value that we got was equal to or larger than 0.66. In our case, this happened 2 times, and we did in total 100 runs. So in 2 out of 100 runs, the mean difference was greater or equal to 0.66, and this gives us a probability of 0.02. And this right here is our p-value. So it tells us the chance of observing a mean difference of 0.66 or greater if the mushroom color didn't matter. And now because this chance or this p-value is so small, we can say that it's unlikely that the mushroom color does not have any effect. And so we can reject this null hypothesis, and we can say that probably there is a relation between the mushroom color and its psychedelic effect. So what we observed is probably a real effect and not just due to chance. Okay, now let's also walk through this in Python. So in this cell we're generating our fake mushroom data, which we can also look at. So here we have a density plot for the psychedelic effect, for the brown and for the rainbow colored mushroom, and just by eye it's a little bit hard to tell if there really is a significant difference. So we formulate our null hypothesis that the color of the mushrooms doesn't matter regarding the psychedelic effect, and then we define our model, which is just a shuffling of the values. So in here we're actually permutating the colors, then we group by the colors and calculate the means, and then based on the means the difference. So let's run that one time. This gives us 0.13, and now we repeat it a bunch of times. So we're gonna shuffle and then apply our test statistic for 10,000 times, and then display our result with a histogram plot. So from this we can read what kind of difference values we would expect to see at which likelihood if the mushroom color didn't matter. We also call this distribution the sampling distribution, but rather the approximation of the sampling distribution, because the real sampling distribution would be the distribution of test statistics applied to real samples. And in here with our shuffling, we're just generating fake samples. And now given this distribution, we want to check how likely it would be to observe the effects in our original data, where we assume that color does matter. And so we calculate that difference value and then plot it as a vertical line, which can already give us some intuition about how likely this value is. And now to calculate the p-value, we take the sampled differences, and then from these only the values that are equal to or larger than our original effect, we check with length how many of the values meet this condition, and then we divide that value by how many samples we had in total. And this gives us a value of 0.0223. And from intuition we can say that this value is very small. But now you might ask, at which point do we say that a value is significant, and when do we say that it's not? And in statistics, a significance value of 0.05 got established throughout the years, but also this value should be taken with care, because it might not make sense to say that a value of 0.04 is significant, while a value of 0.06 is insignificant. So some people suggest that, for example, if the value is above 10, we say that there is no effect. If the value is below 1, we say that probably there is an effect, and if it's somewhere in between, then we just say we're not sure. As a disclaimer for linear regression, in order to apply linear regression, we usually have to meet a lot of assumptions. And if you're interested, you can check out these assumptions in here. But also as a second disclaimer, even though not all assumptions are satisfied, linear regression might still make sense and can give us some insights about our data. Okay, as a recap, today we talked about inferential statistics, which is about making conclusions about our population based on some sample. And we can do so by building a model that captures some patterns or relationships in our data, and then to check if the things we found are actually significant, we make use of hypothesis testing. And when we do hypothesis testing, we actually don't have to care about all these tests with their weird names, but we can just formulate a null hypothesis, simulate data, and then compare the test statistic applied to this data to the test statistic applied to our original data to see if the effect that we observed is real or probably just due to chance.